Now, before I introduce our next speakers, I just want to review our agenda again. We are now starting our 11 a.m. presentation with carbon ink 3D printing. After this presentation at noon Pacific, we will have a 1-hour lunch break, and we'll resume the afternoon at 1 p.m. Pacific with a presentation from the University of California, Santa Barbara, and we'll conclude today's event with our presentation from RheoSense. Just a reminder, if you'd like to stay connected, please follow us on LinkedIn, Twitter, and or Facebook. It's a great way to stay up to date with all the rheology and viscosity news and updates. It's also a way you can connect with our team, or if you need help connecting with our speakers from today, we are happy to help connect you. If you have any questions throughout the presentation, please drop them in the questions panel. We will be sure to answer them at the end of the presentation. All of our speakers have set aside time to answer everyone's questions that come through. So just drop them as they come in, and then at the end of the presentation, we'll get to all of those questions. Now it is my honor to introduce our next speakers, Jordan Bergenfeld and Vikram Palagummi from Carbon. Jordan is the Senior Manufacturing Process Engineer at Carbon. He earned his Bachelor's of Engineering from Georgia Institute of Technology. He studied nuclear energy concentration and fusion system clusters. Vikram is the staff research scientist. Vikram earned his PhD in mechanical engineering from North Carolina State University, where he studied and focused on low-frequency vibration energy harvesting using diamagnetically stabilized magnet levitation. Carbon is a 3D printing technology company, and today we have the pleasure to learn more about Photo-Rheology, a tool for predicting performance and accuracy of 3D printed materials. And without further ado, it is my honor and pleasure to introduce Jordan and Vikram, and I will pass it over to you, Jordan.
Hey, thank you very much. Let me just share my screen. Okay. Is everybody able to see my screen?
Yes, it looks great.
Okay, awesome. Thank you very much. Yes, thank you for that introduction. We are stoked to be here to be able to present at this conference. So I figured we'd start by just introducing the agenda. So we're going to introduce Carbon, introduction to our Photo-Rheometer, measurement capabilities, measurement and derived knowledge, Photo-Rheology, which is a new topic that we're working on, and our conclusions. I wanted to start by introducing what Carbon does. So Carbon, we are a 3D printer manufacturer. So I have a image of our 3 production printers. We have our M1, M2, and L1. And actually, an hour before this meeting, we just launched a new printer. So I have not updated this slide yet, but we just launched our M3 today. So that was some exciting news for today as well. But just some synopsis on what these printers are. So our M2 is our workhorse printer. So this works from prototyping to mass production of parts. We have really fine control of our threads, internal channels in our parts. We have our L1, which is optimized for our high production parts. So this is what Adidas and some of our partners use for making either a large number of small parts or many of large parts. So we wanted to highlight just what our technology is. So Carbon uses a DLS system. So that stands for digital light synthesis. This is where we use our light and oxygen combined to cure our resins in a particular way to have isotropic material properties. We get better surface finish, so you don't get those layer lines from other SLS or SLA printers. We have excellent mechanical properties. That's due to our materials team working on, we develop all of our resins internally. We also do partner with some resin developers to integrate their products into our regime. Wanted to also just start off by giving a video of our technology so you can see our platform coming into our pool of resin, and you can see a part being grown out of this bath of resin. We'll see in just a moment. So this is enabled by this DLS technology where we're able to have a dead zone over our cure front, which enables the resin to flow under the part and be continuously printed. So it doesn't have to be paused to slice between, and we're projecting a full plane at a time as opposed to a single point like other technology.
Yeah, thank you, Jaron. So I'll briefly start talking about the rheometer and the PhotoRheometer part. PhotoRheometer that we have at Carbon, and how we use it to understand how our material cures and how our material performs, and how the measurements that we do on like a single slice on the PhotoRheometer translates into how a full-scale product performs. So what you see over here is a Anton Par rheometer that we currently use. It's an MCR 302. Because we are primarily interested in understanding the UV cure kinetics, so we essentially take out one of the light engine from our printers and stuck it beneath the rheometer. Obviously, we need to also have to figure out how to integrate the controlling of the light engine with the data synchronization from the rheometer. So we use Labview to do that, essentially to talk to the rheometer software so that we can trigger the light engine at the correct time, at the correct interval, to know when the light is on, to basically differentiate the data from when the light is on and when the light is off. So essentially that's essentially the gist of the system. But there is a lot of details in the Labview code that help us play around with the light engine of how it is curing and things like that, which I'll go into a little bit more. In terms of the measuring systems, we generally always use a parallel plate measuring system because if you have seen the videos before, it's essentially although we are a continuous curing, we have a continuous curing system, but it is if you imagine to pause the curing system, it's essentially still curing some amount of layer with every delta T that is added onto the system. So we're still interested in understanding, like at the 100 micrometer slice level or even 50 micrometer slice level, what is the curing kinetics for a given period of time. So for understanding that, we do believe that the parallel plate system is the best for studying this kind of printer. Go to the next slide. Yeah, so just giving you a snapshot of the Labview system that we have. Essentially, we can control everything in terms of the light engine from the Labview code to mimic whatever is happening in the printer. For some long prints, for example, the temperature of the LED may be higher, and that might shift the wavelength of the light. So we try to even test curing of those materials at those extreme conditions of the light engine. So the panel that you see on the left is like controlling different aspects of light engine, not just intensity, the current, and whatnot, to make sure we are trying to mimic always trying to mimic what exactly is happening in the printer, the extremes and the nominal conditions. So that goes also along with what is happening to the light engine. What we also try to do is, as you saw in the video, even though, example, this is like if you try to pause the printer and show that the first slice is being cured, and then the platform comes and kind of moves the slice up, right? So, but the light that is shining on the new layer of liquid that just came beneath it, there's some light passing through that new layer into the previous layer. So all this additional amount of dosage, light dosage that is coming onto that slice one that you see here, still is going to affect the final kinetics of the cure over there and the mechanical properties of that layer. So we try to use the Labview code to have like this true multi-dose cure. So to accurately mimic everything on the rheometer, mimic everything that is happening on the printer. What you see, there are a few designs that are there in the bottom, circular, a 4-quadrant, and kind of a hashed out pattern. Sometimes it is beneficial to not fully cure the layer. Probably it's best to cure only part of it. There are scenarios where you would want to use the same material, but probably want to achieve slightly lower mechanical properties, or you would also want to reduce some of the shrinkage forces in the material. So these are techniques that are widely used in SLA, and this is something is also of interest to see if we can use this kind of technique to fine-tune the final material properties and product properties. If you go to the next point, we also, as you were seeing in the previous slide when Jordan was showing you the video for the printer, the platform that was moving was black in color. So we also wanted to mimic that kind of a black platform. Why that is important is because if you have like a conventional measuring system, a parallel plate measuring system from many companies, it's just a pretty shiny aluminum plate. So what it does is it reflects the light back when you're trying to cure it, and so that is kind of adding more dosage into the adding more light dosage into the material, which is not what is. So it's by doing that, it's not replicative of what is happening in the printer. So we use anodized plates to kind of reduce that reflection and mimic the intensity profile more accurately on the rheometer. In terms of the way we use the rheometer, essentially the figure on the left here kind of gives you a snapshot of what is happening. So we have like a, say, 100 micrometer slice or 200 micrometer slice of material, and we're shining the light from beneath the glass. And as soon as the material starts to cure, there is some shrinkage in the intrinsic shrinkage in the material coming from the conversion of the double bonds into linear chains. So once that happens, the material is also trying to cross-link and trying to develop modulus. So it's trying to shrink as well as apply a force on the rheometer shaft. So there's a normal force that's exerted there. So the rheometer can respond in many ways, but I just essentially stated two key ways in which we generally use the instrument. One is called as the zero normal force mode, where as soon as the instrument sees that the material is applying a force on it, it tries to move the top plate to kind of reduce out the force to zero. So in that way, we are trying to capture the full shrinkage of the material. That in itself is a useful amount of information for us when we are doing some new material development. We always want to track how much of a shrinkage is there in this material as compared to what the modulus is. So just in this one mode, the instrument gives us very useful information in terms of the modulus development as well as the shrinkage in the material. And this is all very all the data that we get is only very relevant once we have accurately mimicked the intensity intensity that is similar to the printer onto the rheometer. So that's why I was focusing more on the last slide about how closely we're trying to mimic the intensity profile. The second mode that we use is called as the fixed gap mode. The term the fixed gap mode is it's not true in its sense, as in it's the intention of the instrument is to when it's say if the experiment is starting at say 100 micrometer slice, and when you're curing the material, there's some amount of shrinkage, and say there is say 4% shrinkage, so the material gap from 100 microns goes down to 96 microns. So but in the fixed gap mode, the instrument is trying to maintain that gap to 100 microns. For example, we try to say, okay, from the beginning to the end of the experiment, try to keep the gap fixed at 100 microns. So, but in reality, the rheometer shaft has some give to it. So in that, what I mean by give is there is some compliance to that shaft. So in our instrument, the compliance of the shaft is 0.59 micrometer per Newton. Compliance is also, you can think it of as the inverse of the stiffness of the material, stiffness of the shaft. So because of it being compliant, when the material is pulling on the rheometer shaft actually in microns or nanometer level does get extended. So in this way, I mean, because it gets extended, it's not truly trying to maintain the gap to be fixed at 100 microns. But this is a very useful mode for us because it kind of gives us an idea of how much force the material is exerting, how much stress is in the material, and this is kind of a very important metric for us for some of the things that we try to do, which I'll explain on the later slides. But the main outputs that we generally are interested in are the normal force, the shear storage, loss modulus, at multiple frequencies, and as well as shrinkage, all as a function of time. So as I was mentioning, in a single experiment, we try to use all the data in terms of essentially the crossover point, which is basically the crossover from the storage and loss modulus, the rate of the reaction, the final modulus, shrinkage that is occurring in the material, the tan B evolution. I'll show a little bit of what I mean by all this in the next slide. So yeah, I was mentioning the crossover point. That's kind of a very important metric for us, trying to understand. For example, the figure that you see on the rightmost top over here, you can see that until about time equal to 100 seconds, it's essentially the light has not been switched on. It's we generally collect the data for normalizing purpose. What is the baseline before the material is starting to UV cure, and after it starts to UV cure, it takes about, over here you can see about 1.7 seconds before it crossovers. So that crossover point is essentially stating the point at which the cure front is hitting the top plate. So you can imagine as the light shines, the cure front starts from the bottom where the glass plate is and starts to travel up and hits the top plate. When it hits the top plate, you see a huge increase in the normal force of the instrument, and and you start to see the material and you start to see the shaft adjusting itself to decrease the normal force to 0, and that's when you see the gap change and the shrinkage going shrinkage occurring and the gap decreasing. Also interested in understanding how the storage modulus and loss modulus are changing over time. That's why we also look at the tan B loss factor for these things. We've also try to do like frequency sweeps and temperature sweeps to kind of get like a time temperature supervision plots, but we're still in early stages of trying to see what useful information we can get from it for our printing process. But that is definitely that's something we are trying to do. So because we are always interested in understanding how parameters of the intensity or at what temperature we're photo curing and printing the stuff is changing the actual standard for the materials, and how it is changing the TG for the materials. So that's always of interest to us. So I was mentioning previously about the fixed gap mode and the zero force mode, zero normal force mode. So I was talking a lot about like the compliance of the instrument and how there are forces exerted by the material while it's shrinking. So why that is important is because it all goes back to how it all goes back to the dimensional stability of the final printed product. So if you see the figures over here, like for example, the figure on the left, you can see the part. This is from a YouTube video. It's not from the company. I just picked something to show like a really exaggerated situation of what can happen due to those shrinkage forces. This print shows that the material is starting to peel off from the base plate. That's essentially because of the shrinkage forces that are exerted, and it's trying to shrink, but the platform is trying to restrict it. The platform as well as whatever material has already cured. So that's definitely not ideal, because once the things have popped off in the middle of the print, there's no longer the rest of the print is basically inaccurate, because it has no idea that the part has popped off and what angle it is and whatnot. Even if those parts have not popped off, but you were successfully able to print it, but there is a lot of internal residual stress in the material. And once you take out the part and try to use it, for example, an example over here is like a box and a lid. You can see that the lid is not able to be closed over here because of the internal stresses. The thing has slightly warped enough so that you can't really use it for the case that you intend to use. A figure on the right also shows like a flat part that you're trying to print, but has this curvature. So the idea is, can we use the rheometer to understand at the slice level what are the forces that are there, and can we try to calculate by using that forces and using some scaling factors to see what all is internal stress in the material, and if we can predict what is the likelihood of that material warping or not warping. So here I'm showing you some representative data where I'm showing, so right now it's highlighted, there are 4 different runs in this experiment, in this graph. Right now the circle that over there is showing like 2 of those curves. So what basically we're trying to show is that in the fixed gap mode, where I told the instrument to try to maintain 100 micrometer slice gap, after the material has shrunk, the overall shrinkage is about 5.4%. And click next. And when you use it in a zero normal force experiment, and we are trying to look at the other 2 runs on the rheometer instrument using a zero normal force mode, we see that the shrinkage is about 6%. So it's slightly higher, and that's what you would generally expect, because in the zero normal force, you're allowing the material, you're allowing the shaft to move as much as it wants to make sure that the normal force that it's seeing is 0. That is, there's almost no stress in the material. In ideal case, this would be termed as free shrinkage, but this is the closest we can get on the rheometer to determine free shrinkage. And the previous 2 runs were not exactly free shrinkage, because we are asking the rheometer not to move, but because of the slightly high compliance of the rheometer, it does get extended because of the shrinkage forces. So one could say that the difference in the shrinkage measurements between the fixed gap mode where you're asking the rheometer not to move, versus the zero normal force, where you're asking the rheometer to move. The difference is actually the shrinkage that is being restricted by the instrument because of the compliance of 0.59 micrometer per Newton, which I mentioned earlier. So if you look at the same runs, but if you just look at the normal force runs right now, normal force values, you could see that the zero normal force, as the name mentions, almost a zero normal force. It has this in the initial stages, it has a lot of, it's not noise, but essentially whenever the material is starting to pull, the rheometer moves down to nullify that forces. So it takes some time for the rheometer to find its equilibrium position where there's no normal force. Essentially because it generally overcorrects and then corrects back, and that kind of a process goes on for a few seconds before it finds the spot where there is no normal force. So, like I was saying previously, the shrinkage difference between the like a zero normal force and the fixed gap, the shrinkage difference is roughly 0.6% that was shown on the previous slide. So one could say that whatever normal force value we are getting in the fixed gap mode is essentially coming to the value that we're getting here, about 9 newtons, is all because you're restricting that 0.6% shrinkage. So this is kind of like a good metric for us to understand that, okay, this material when it has a interface, be an already cured material or a bill plate which has a compliance of 0.6 or 0.59 microns per Newton, it is going to see an internal force of 9 newtons. So why do we want to know that? Go to the next slide. So what I'm trying to say is that if on the figure on the left, if you see there are like n layers of parts that are printed and layers of slices that are printed, we can assume that after like some n layers are printed, the part has a compliance of 0.59 micrometer per Newton. Now that is similar to our compliance of the rheometer, right? So we can assume that the n+1 slice, which is being printed, is actually going to have that 9 newtons of force in it. So we can kind of try to use some empirical scaling to understand how that 9 newton force increases or decreases as you're going closer to the bill plate or away from the bill plate. And based on what you're printing, you can try to determine roughly what is the bending stiffness of that part. So the shrinkage forces are caused due to the high modulus of the material or high shrinkage of the material. But the bending stiffness is kind of try to restrict that shrinking that thing. So in a way, the modulus that is developed in the material is actually trying to restrict the shrinkage by giving the overall part some stiffness, but it also gives it the shrinkage force because it's trying to it's essentially the force is coming as a product of the shrinkage that is occurring at a specific modulus. So we try to go through a very iterative process to understand on the formulation side how we can change the kinetics of our modulus and shrinkage to either get a beautiful flat part over here, or at least try to mitigate the warping in the part. So this kind of problem is pretty universal in UV cured 3D printing systems. So and it's been a long, it's pretty a decade old, more than a decade old problem, and it's pretty intrinsic because it comes from the chemistry of materials shrinking. So this is something new that we've been trying to do, and obviously one could say there are like a lot of assumptions going on in how we are using the rheometer to calculate the forces in the part and how that is finally can be predicted to warping of the parts. But I would be happy to hear any suggestions on what else we can do on these kind of measurements, but this is something we are still trying to fully validate, but which had some success till now. And other things that we do with the rheometer, except from the Photo-Rheology, is some kind of stability of the dispersed components, where we do some oscillatory tests at different shear rates to understand stability of some, say, some kind of fillers that are there in the system, and we kind of do like a repeated testing to see how the crossover point from the storage and loss models is changing with time. Is there an yield stress in the material? What is it, and why, if it's changing with time, and try to track and couple these kind of measurements with other techniques that we have in the lab to see what is the stability of those things.
So on another note, we have a recycling process at Carbon, and during this process, we found that we can lose one of our critical components. And using this rheometer, we've been able to create calibration curves and have a pretty linear correlation between rheology and the weight percentage of this component in a solution. So this is using a different geometry than Vikram was speaking about. We use a bobbin cup to increase that contact area for the liquid. And this enables us to implement a QC metric for end of line in manufacturing to ensure we have consistent material composition going out.
Yeah, so the other stuff that we do with the Photo-Rheology is try to bake our parts. So why we are interested in like baking our parts is because with our patented materials, we have essentially two reactions that happen for the materials. One is at the printer during the photo cure, and the other part is in the oven during the thermal cure. So we are interested in, like, we try to see for our new material development, can we understand the not just how the material's green modulus and kinetics, how its shrinkage occurs, is it stable, and all those things at the figure on the left, where you're talking just about the Photo-Rheology part. But we will also like try to put the whole system under high temperature, continuously continue shearing it, and see how the thermal cure kinetics takes place, and how the modulus changes with time, as well as trying to figure out what is the TG of the material after the bake. So this is essentially an important step, because it kind of guides us in terms of our processing conditions for the materials to fine tune our mechanical properties and achieve the goals that the materials can. So it kind of tries to give an early hint in the material development of what kind of bake kinetics, bake temperatures, and what are all the different parameters that need to go into it to achieve good properties. Go to the next slide. So here I'm just showing you like a representative data where you can see the curing part and the initial stage of the photo curing part, where you see the storage modulus increasing something close to like 10 megapascal or so, and then you're starting to heat the sample. So now, especially if you're thinking about temperature, initially it's a room temperature. There's nothing such as room temperature. I understand it's a 25 C over here. We photo cured at 25 C and then ramped up the temperature to 180 C and just hold it at that temperature. So what you can see that immediately after you start to ramp the temperature, the modulus goes down and essentially is zero, right? So this is not necessarily a good thing, because we know that most of the thermal reactions are latent in nature. They take some time to kick off, and we depending upon what temperature it is, they may take different amount of time to actually start developing the network. if you think about why those things are important and what temperature you need to heat and how long you need to maintain the temperature. If you think about like an actual part that is printed and then put it in the oven, right? If you heat it up like really quickly, okay, and say the materials modulus is only 20-30 megapascal, and it has a TG initially in the green state to be 30-40 degrees. So what will happen is if you immediately ramp it up to like say 150 degrees, where the thermal network will develop, right, very quickly. So if you do that, what you'll see is the material initially becomes so soft that it loses its dimensional stability. So the idea is, can you find out a ramp temperature before you really accelerate your thermal network to develop enough modulus in the material so that it still holds its shape while the thermal network starts to build. So these things are kind of important to to maintain the dimensional stability of the part as you're thermally baking it. So a figure on the left, figure on the right, where I'm trying to just show like the Q kinetics at 160C and 180C. So we generally do a lot of tests on our materials to understand how those Q kinetics vary with temperature and what kind of different steps we need to different steps of temperatures and different hold times at those temperatures we need to set to maintain a minimum modulus of the materials. For example, if I know that my part is going to sag, if the modulus is say 10 megapascal, I'll make sure that my ramp temperature is such that I never go below that modulus value and still maintain the dimensional stability of the part as I ramp up to higher temperatures. So these kind of runs on the rheometer are a good way for us to check at what temperatures the material is actually losing a lot of its modulus before its thermal network starts to build. So those are the main kind of things that we try to study, and understanding and optimizing how we need to cure our materials to better develop its properties. So in summary, I would say that the primary focus over the last year has been to set up this instrument, validate it, and incorporate it into our material development programs. And essentially, we like to understand from its uncured, photo-cured, and break properties to further fine-tune or optimize our materials. And it is used a lot to as an initial screening technique for new formulations as well, which can, because it's such a small scale, it can help us run through different screening, run through a lot of formulations before we start to actually print parts and try to see its actual bulk properties. But from all the good data and good adjustments that we could do to the instrument, we still want to improve the gap resolution within the photocooling process. You might have noticed in the previous figures where when I was showing you the gap versus time, there was a lot of still noise in the. I wouldn't say noise because it's essentially because the resolution of the linear motor over there is only about 0.6 microns. So to make sure that the normal force goes to zero, it either tries to go up 0.6 microns and below 0.6 microns to find the balance where the normal force is zero. So it's not fine enough for most of our measurements, but it's something that we live with right now. Another thing that we would love to have is have different measuring systems, have similar measuring systems, but have different compliance. So that's something we're trying to see if we can try to mimic that, because essentially, as I was saying since the starting of the talk, we're always interested in understanding, mimicking things on the printer. So we know that the compliance of the printed layers are different at different thicknesses. So we always want to mimic that on the rheometer, but currently we're fixated to the 0.59 microns per Newton. Also, right now we currently use the rheometers limited to about 200 Celsius, minus 40 to 200 Celsius. But we generally want to go like much higher temperatures to further improve, further understand like at higher temperatures than 200 C, what is the curing kinetics of for thermal networks. Yeah, with that, I think we kind of gave you a good overview of the rheometer that we use and how we have modified it and how we are using it in our optimizing our current material formulations or in the new material developments. And I would be happy to take any questions.
Thank you both so much. So we did have some questions come in, and if anyone has additional questions, again, please drop them in the questions panel, and we will take the next 15 or 20 minutes to answer everyone's questions. So the first question was referring to topic 4, why is tan delta starting at a very low value at 100 S? Isn't the sample a simple Newtonian liquid at that stage with a tan delta approaching infinity?
Oh, that's actually right after the material has cured. It's not in the liquid state. I kind of cut off the data, but you're right. Like it's immediately after the material has just started to cure.
And then someone else asked, have you tried measuring orthogonal, shear, and axial rheological measurements?
No, that's a good question. I was actually starting to talk to the company regarding that, but we have not really done those kind of measurements. And it's really interesting because as you can imagine, it's not just when the material is printing, it's just not the axial forces, but there are a lot of orthogonal forces that are definitely part of the printing process. So that's a really good question.
And someone asked, is your post-light and or post-bake polymer amorphous, semi-crystalline, or crystalline?
Oh, sorry, can you repeat that?
Is your post-light and or post-bake polymer amorphous, semi-crystalline, or crystalline?
I would say semi-crystalline. That's a good answer.
And what is the typical frequency the cure profile experiments are run?
Because we want to get like a good number of data points, we generally do 10 hertz. But yeah, I mean, if you go anything more slower than that, we probably miss the kinetics of the cure, because these things cure within like 2 to 3 seconds. So generally we fix at 10 hertz, but we have data for all different frequency ranges.
And someone's asked, I understand that you start the rheological measurement in a linear viscoelastic region. Does the material show nonlinear viscoelasticity as the curing progresses?
Yeah, so so based on the strain value that we're using, we're using a pretty low strain value of 0.01% generally, and we have seen for the cured material, we try to do like a amplitude sweep and see where the nonlinearity is kicking in. So yeah, we generally have to initially do few amplitude sweeps to figure out what is the nonlinearity region and use the minimum value in the linear region for the whole cured sample. So yeah, I mean, if we are using something like say 0.1% or 0.5% strain, yeah, then definitely you're hitting the nonlinear region for the material in the cured state. So we do consider that. Yeah, these are all really good questions.
And again, if questions come to you, please don't hesitate to drop them in the questions panel. And I'll give everyone just one more minute to ask any additional questions that they have. Someone asked, have you tried curing at a higher normal force, so say greater than 0?
Yeah, that's a good question. So yeah, we did try, but we try to exert that normal force a little bit into the curing, because if you exert that normal force right from the start of the experiment, then the gap is going to be decreased, because it's essentially a liquid, and any amount of normal force is just going to change the gap. So we try to exert the normal force a bit after the curing to see. I'm assuming your question is based on like how do you know if you have like good contact or good adhesion between the material and the sample. So we tried exerting like small normal forces after the material is slightly cured. So after that, we measure that modulus value with the one where we don't apply that normal force, and it's essentially the same for the materials that we tried. I mean, you don't want to go like too high, like even anything, I would say anything above 0.5 newtons is, you're starting to apply the stresses in the material, and the modulus value starts to change with that additional stress in the material. So yeah, we have tried it, but the zero normal force in terms of trying to it's in its effort to try to reduce any stress in the material, I think is good enough for us, those measurements. But I would only add that we try to, for reasons we are still trying to explore, we try to apply a normal force function on the material. So say as the material is curing, we try to exert some amount of normal force, so that we're trying to mimic as if the shaft is of a lower compliance. That is, if the shaft is of a higher compliance, it exerts a higher normal force. So what we do is we initially have a function where the normal force starts to increase, but not enough so that it's kind of like pulling up the material. And after the material is fully cured, we apply a significantly high normal force, say 10 Newton. So that kind of mimics what happens when the material sees a much more stiffer interface. So we tried playing around with those things, but we're not yet super confident of how we can trust those results yet.
Is the curing rate dependent on viscosity?
Yeah, I mean, it depends on the mixture of like the oligomers and diluents that you have. If the person who asked the question knows like general oligomers, like say bis GMA, which is a bisphenol A based methacrylate, which is a really rigid polymer, a rigid monomer. So if you try to react that, its viscosity is like really high, it gels pretty quickly because of diffusion limitation. But if you compare that with something like a triethyl glycol dimethacrylate, which is very low viscous, right? So its reaction rate is really, really slow before it gels. So yeah, viscosity is like very, it's a pretty well-known thing that it's going to really impact the curing kinetics. And based on what monomers you choose, your final modulus and all that is going to check them out.
Is there an optimal viscosity range for your polymer?
There are ranges that we try to keep our monomer composition in certain viscosity range, but we can also I would say that there is a range, but on top of my head I can't exactly tell what that range is. But yeah, there is a higher limit where we don't want the viscosity to be too high, because you can imagine like in this kind of a process, when the build platform is moving up, if your viscosity of the material is too high, things don't flow in for the new layer. So we definitely want an upper limit on that viscosity.
Someone's wondering have you found solutions to the warping?
So we have solutions. it's right now the solutions are part specific or for some materials. So it's still work in progress. Like as I was mentioning, warping is like a universal problem across the industry. So everybody is making small steps of progress every year. So we are in the same cycle.
And again, just to make sure we don't miss anyone's questions, I'll give everyone one more minute just to drop their questions in that panel. And it doesn't look like any more coming in, so Jordan and Vikram, I just want to thank you both so much for joining us today. This was such a wonderful presentation, and I know I personally learned a lot about 3D printing and your processes.
Yes, thank you for having us. We really appreciate it.
Yeah, thanks for the opportunity.